यहाँ जायचं का है सुने नहीं आ रहा है क्यों यारी
Okay, hello and welcome to our course, Engineering Mechanics 2. There is still a few more students who seem to drop into the course, but I will start now discussing the organizational part of this course. So first of all, as you know, as you see, this is an online course. There was a voting where you could vote for either online or on-campus courses Thursday last week, and out of 138 students, 98 participated in the vote, and 2/3 of these students said that they prefer online classes. And that's why we switched to an online class. In my opinion, it would be much easier to learn and to study in this course if it would be in presence, because it would be easier to talk to me and I could have a look on your computations and help you. It would be just easier for you and maybe simpler. Anyways, you chose online, and that's why we have online classes on Friday. So our Friday class is an online class throughout the whole semester. On Monday, you can choose between online or on-campus classes. So, because in my opinion, on-campus classes in presence, talking to each other, will help you a lot to learn, to study, and to get used to the whole life at this university here. So if you're not in Schweinfurt, take the course online at what time is it? 11:45. And if you're here in Schweinfurt, I recommend to attend the course in presence at this time, 2:15. Okay. It is not in the. Actually, I don't know which number you have, which room number you have for this on-campus course, but it's stated in our e-learning course. And I can tell it to you as well. Of course, it's at in 1E31. Just there's a question in the chat. No, I will not record the lectures. So this is not allowed. Okay, so What else? What we will do is we will do the same, of course, on Monday in the online class, in the on-campus class. So you will not miss anything if you choose either one. And so we will discuss theory, mainly theory, on Fridays, and on Mondays we will practice the theory we learned. Okay, any further questions so far? Okay, if not, then there were quite a lot of you who picked up the lecture notes today. The course schedule, well, the course schedule is on your student schedule. You should have it on your class schedule for all the other classes. For online and offline, Fridays are online classes, always and only online. We will mainly, not only of course, but mainly discuss theory and have a look at the type of problems, the type of exercises we will solve. And on Mondays, we will practice the theory. So we will solve the exercises. Okay. And there are 2 classes on Mondays, one in presence, one online. It's all written in the e-learning course as well. The course schedule, so the class hours as well. One course is online, one course is offline, and we will do the same in both courses. You can attend both, of course, if you like, but you will not miss anything if you attend only one of them on Mondays. But all of you have to attend the course on Friday, the online course on Friday. Yes, Monday is side by side. Okay. Other questions?
Sorry, I'm a bit confused, Professor. On Monday, the 2 classes are the same classes?
Yes.
The same topics? We would.
Yes, Monday is the same. For the students who are not in Schweinfurt, they can only attend the online course, of course. And for the students who are in Schweinfurt, I recommend to take the offline course. Okay, but we will do the same. Okay. Further questions?
I have a question regarding to the tutorium. In the e-learning, it says it's additional and it's at 2:15 on Mondays, or is it because 11th of October is a Monday and then we have class also?
Is it
How
the
is
German
that done?
tutorial?
It just says it in the e-learning of engineering mechanics too,
And
that
is
there's an additional tutorium in Schweinfurt
Oh, in the
starting
e-learning course?
October 11th. Yeah.
Oh, then no, that's sorry about that.
I
That's
can
not
copy it into
the
the
case.
chat.
Yeah, no, I just I trust you. Then this is probably just the information from last year who was not erased.
Okay.
Just a
Thank you.
second. Yeah. No, because it wouldn't make sense to have a tutorial at the same time, of course. Okay. Well, I will check this later on. My computer needs some time loading right now. Okay, then for the class materials, a lot of you already picked up the class materials. Oh wait, there's another question there. Oh, okay, yeah. Picked up the class materials already. For the ones that are not in Schweinfurt, you have to print it yourself. And if you are in Schweinfurt, you can also pick it up on Wednesday this week, or I will bring some of them to the offline class next Monday. What you need and what you need to print, or I recommend to print, are the lecture notes, okay? So these A4 pages, because there are blank spaces, and we will fill these blank spaces throughout the class, okay? And if you're not able to write on your computer and fill the blanks there, then you should print it out. It makes it much easier for you to learn. Then the exercise book. Of course, you do not have to print the exercise book if you don't want to. You can look the exercises, the problems up on your computer. So this would not be necessary. There's a question. The PDF files are in the online course, in the e-learning course. They are there already. I'm not sending them. They are, you just have to download them. So if you have a look in the e-learning course, the first, like after below the announcements, there's the documents, and there you will find lecture notes, exercises and solution, I think it's called, and old exams, and the formulary. We will see. Third document you need is the formulary. Again, if you are in Schweinfurt, pick it up, or if not, you can print it. We will work with this formulary a lot throughout the whole semester, but please keep it for the exam, because you can bring the formulary to the exam. Don't write in the formulary, and only in the last 2 pages, pages 9 and 10, I'll show like this. There is a blank space, blank page, and there it's written individual notes, and there you can take notes. Okay, only there, not on the other pages. So just I think it would help to print it already and work with it. But if not, you don't have to. If you are not able to bring it to the exam, I will hand you one there. So for the students who are not yet in Schweinfurt, if you come to Schweinfurt to take the exam, I will have a formulary for you. But of course, then there are no notes inside.
Excuse me, Professor, I have a question.
Yes.
Because there was a confusion last time when we were giving the last mechanics exam and we did not have clarity. So I just want to confirm that apart from this formulary, are we allowed to make our own, or how many A4 pages are we allowed?
Okay, so if you have this formulary, it's in A5 format. And in this formulary, there are 2 pages for your private notes, for your individual notes, page, 10 and 9, okay? So if you don't have a formulary, you can write your own notes, but on the same space. So you can use one A4 paper, one-sided, and take your handwritten notes there. They have to be handwritten, and they have to be there just 1 page, okay? Not 2 pages of 1 paper.
Understood, thank you.
Okay. Yes, if you are not able to pick it up on Wednesday and haven't picked it up yet, you can pick up all the stuff next Monday at 2:15 in 1E31. Yes, for the private message, the answer is yes. Okay. Other questions regarding the organizational stuff? Okay, if not, then let's talk a little bit about the class and the content of the class. In this class, it's similar to Engineering Mechanics 1. There's not that much theory you have to learn. So we have plenty of time to do exercises, to practice what we have learned. But you have to work, and you have to solve exercises on your own. If you only watch me solving exercises, it will seem very easy, okay, and very simple. But once you start solving these exercises on your own, and if you start solving this for the first time just a few weeks prior to the exam, you will get in trouble, okay? Just for those who have not done statics, well, probably yes. You might have some difficulties in this course. If you took statics and understood statics but haven't taken the exam yet, that will be okay. But for example, you have to be able to build the equilibrium conditions. That's a basic thing that you learned in statics and applied many, many times for the different problems. And we will definitely need this here for a lot of problems as well. No, it's not engineering Yeah, yes. This class here, oh, maybe it's now called Engineering Mechanics 3. In the last semester for, yes, this is the dynamics class. So it was, it always had been Engineering Mechanics 2, because you only had 2 Engineering Mechanics classes, but maybe there was an update because in other classes, there are 3 Engineering Mechanics courses and dynamics corresponds to the 3rd one. Okay, so this is the dynamics class. Okay, let's get back to the content of the class. So as I said, it's important that you solve, okay, that is for the new students. No, 3rd semester students. You have Engineering Mechanics 1 in 2nd semester, statics, I think. And then, so last semester, if you're on your curriculum on time, and then this is the dynamics course for 3rd semester students or older, but you have to have heard statics. Okay. He's a colleague. Why are you asking? Yeah, interesting question. Okay. Maybe, well, okay, you haven't been on campus yet, probably, so might be your first day today, but you always have 2 professors in one office. So we are sharing the office. Okay, now back to the content of this class. Okay, yeah, well, maybe one more thing, because you might have heard from all the students, or probably some of higher semesters are in this course right now as well, that this class is really difficult to pass. And yes, it is, but it depends a lot on how you work in this class and how you study for the exam. And I'm repeating myself a lot of times. I did the last semesters, and I will this semester. There are, of course, many students who fail the exam, but on the other hand, there are a lot of students who pass the exam on first attempt with really good marks. And one reason students fail the exam is because they don't have the basic math knowledge. Okay, so if you realize that you have difficulties in mathematics, you really have to work on that, because otherwise it will be really hard to pass the exam. And I mean basic math, okay, no higher mathematics. I mean things like rearranging equations or canceling terms in equations, or changing dimensions from kilometer per hour to meter per second and things like this. Okay, but many students fail because they are not able to do this. And if you're not able to do that, you will not be able to solve any of the problems given. Okay, so you have to work on that. And if you see that, if you realize that you have trouble there, you can talk to me, or you can do extra practice or whatever. Okay. Another thing is you need to be able to read the drawings. So if you have a look at the exercise book, there are always figures given, like systems with blocks or cylinders and connected by ropes or by joints moving them. And you have to understand the drawing. And this means you have to see the drawing, and you have to be able to understand what happens, how the system moves. If you cannot derive the way of motion, the type of motion of a system by looking at the drawing, again, you will also not be able to solve the problems. But of course, you do not have to be able to do this right now. We will practice this throughout the whole semester. But practicing means you have to work. You have to solve problems on your own. And for this, we have the Monday class, okay? And if you're in Schweinfurt, attend the course offline, and I can walk through the rows, I can talk to you. And if you're online, if you choose the online class, please try and please talk to me as well. You can talk to me in private if you don't want to talk in front of the class or whatever, but you have to talk to me. You have to show me what you're doing. Otherwise, I cannot help. Okay. And giving you my solution will not help you. There are several ways to solve a problem, and you have to find your own way of solving the problems. Yes.
Yeah, I had a question that about the lecture on Friday. It's going to be online, but what if there's a clash with other subjects? Like I have one of my core elective at the same time, and
yeah, there's nothing actually we can do about it, because the schedules, the class schedules, are made for the individual semesters. So if you have courses from different semesters, this happens that they take place on the same time. So
this won't be a possibility to just record the session on Friday, because I'm sure there will be a lot of few other students as well that they might struggle with the same problem.
No, well, on Fridays I will try to only discuss the theory. Okay, so we fill in our blanks in the lecture notes, and then you can talk to your classmates to copy them. The Monday classes are really important.
Yeah, okay, thank you.
Okay, so I just have to go through the chat. Yes, I'm always showing you the solution path, and I'm solving full problems for you, as I did in the last semesters as well. And we will discuss that. But of course, every problem is different. And what you have to learn is the basic method. So I will provide you with step-by-step procedures. Okay, so you have to, there are only a few different types of problems, not many. Okay, we are only distinguishing, for example, between a point mass and a rigid body. And if you're able to do this, choose whether it's a point mass or a rigid body, there's only one method to apply, and it's always the same method, the step-by-step procedure you have to apply for solving the problem. And I will show you this full method applying to a problem from the exercise book, and then you have to apply the method to other problems as well. Okay, we will practice this, of course. For mechanics too. So we are talking about dynamics. Well, you have the exercise book with a lot of exercises, of course, and you can go to the library and get literature there. No, the exam is only on campus. Yes. Okay. No, I think we have all the questions. Okay, other questions? No, I cannot. I have a full plan the whole week, and also we do not. How am I? We are 290 students. How am I supposed to find the date that suits all of you? That's not possible when switching the lecture. This lecture suits all students in third semester because that's when it's regularly taking place, and it's not possible to change. Okay. I don't know yet. We are still looking for a person who might do the tutorial. I see 5 students. Well, our class on Friday, I think, takes place at 11:45. No, I can't move any of the 3 classes because I don't have a lot of other options, and there are no options that suit all of you. Well, we could take.
Professor,
yes.
Could you just upload the field script? Like, suppose you wrote whatever you explained in the class on Friday. If you upload,
yes, I will upload the script, but maybe not every Friday. Maybe more like when I finish the chapter or something.
Yeah,
like that.
then it will be useful for everyone.
Yes, of course.
Missing, then we can catch up.
Yes, yes.
Thank you.
Okay. any applications? What kind of applications? You want to? No, not in this class. You can, of course, if you like, use Python. I think you had a Python course already, or at least some of you, for like solving problems or something like that. But this is actually a mechanics class, so it's all about performing computations, understanding how a system moves, and computing velocities and accelerations and distances traveled, work performed, energy applied, these kind of things. Okay. All right. Okay. I think if there are no more questions, we can. Yeah. Okay. I don't know. Just the professors are not giving tutorials. Okay, so they are. We do have several exams or exam problems from the last semesters or last years, actually, in the exercise book. But maybe we should just start with the class and not think too much about the exam yet. I will remember you on what you have to do regularly. Yes, exactly. Yes, for the private message, several actually. Yes, I know, but he's probably not able to give a tutorial. Okay, I can talk to him, but I don't know what his answer will be. Probably not. Okay. Okay. Now let's have a look at the lecture notes. And start with the class. Okay, so Engineering Mechanics 2, or maybe now 3, if it was changed, I have to check that, but in my schedule it's still called Engineering Mechanics 2. And okay, we have the table of content, of course. I will not spend too much time on that. We will basically distinguish between two different types of motions, or we will discuss point masses and rigid bodies. First, we will discuss kinetics, meaning distances, velocities, accelerations, and then we will discuss the kinematics. So once we know the velocity and the acceleration with which our object moves, we can describe the forces, the loads acting on the system. So that's what we will do in chapter 2. And in chapter 3, we will talk about like work and energy, efficiency, power, all these kind of things. So we know the loads acting on our system, so we can compute the work performed, the energy applied, etc. In the 4th chapter, we will discuss the point kinetics again, for the principle of D'Alembert, and solving these problems according to the loads acting on the system. And chapter 5 is a really short chapter. We will discuss how to compute the characteristic values of mass. What this is, I will explain in detail in a couple of weeks. Chapter 6, then the kinetics of rigid bodies. So again, you see the distinction between point masses and rigid bodies. But for every one of these, we have our step-by-step procedure to solve the problem. And then our last chapter discusses the principle of linear and angular momentum, meaning impact problems, etc. Okay, now for this course, what is dynamics? Dynamics is the study of motion of point masses and rigid bodies, and the context between motion and forces. So what forces act on our system when the object moves as it is described. And we are only discussing point masses and rigid bodies. So non-deformable objects would be a bit more complicated if our objects would be deformable. But we will not discuss this in class. Then what is a point mass? You know this already from statics. A point mass is a point with no specific spatial dimension, and it's only just a small point with an assigned mass. And the body then, of course, is in a closed domain with identical material properties. So we have spatial dimensions, a length, a width, a height. And dynamics is all about Newton's second law. You heard about the Newton's the four laws of Newton in statics and engineering mechanics 1. So the second law states that the force acting on a body corresponds exactly to the change in motion of our body or our object. It will not be only one body later on. It will be more complex system. Okay, now we will start with the simplest form of motion. As I said, kinetics is discussing the motion of the object, and now we will start with point masses, and we will start with the rectilinear motion. And this means that our object, our point mass, moves along a straight line. Okay, so for example, I just have to move this over there. So for example, if we have a road, and there's a car, oops, on this road, and now we watch the motion of this car. Then there is this moment when we start looking at this car, watching the motion of the car. So this is our start time, t0, maybe at 0 seconds. And then this car has a certain position. Okay, and the position, well, just if we talk about point masses, we simplify our car to just one point, the center of gravity, and describe the motion of this point mass. Please don't draw into my lecture notes. Okay, so now this car is at a certain position. Since it's our starting position, we call it x0. And in this instant of time, the car moves with a certain velocity and acceleration. Velocity, acceleration A. Is there a question? Okay. And then we can record the car at some point later in time. Then it might have moved over here. The time t. No, the car is not at rest. It moves with a velocity v0. Okay, and now this car is at a different position, of course. That's position x at the time t. And it might have a different velocity and a different acceleration. So we have the velocity v at time t and the acceleration a at time t. And now we need some equations to describe the change in motion, to compute the distance traveled after a certain time interval, for example, or the velocity reached after a certain time interval when driving with a specific acceleration. These kind of problems are the type of problems we want to answer at the beginning. Now, for this, we need a sign definition. We need to define which direction is our positive direction and which one is our negative direction, because we have to sum our vectors according to the to the correct sign, as you learned in statics. There you added forces, and now we will do the same with accelerations, velocities, and distances. Okay, for example, in this case here, it would make sense to define the direction pointing to the right as our positive direction and to the left as a negative direction. And that is the most, or the direction that is most often used, okay? So I will write it like this: pointing to the right is the positive direction, pointing to the left is the negative direction. Once you chose your positive direction, it has to be applied to all three variables: distance, velocity, and acceleration. Again, very similar to statics. In statics, you build the sum of all forces in horizontal direction, for example, and you said you will sum the forces pointing to the right as positive forces, pointing to the left as negative forces. Okay. Now, how do these equations look like? So I think you remember them from school, from your physics class. And so to compute the velocity, when you know the distance and the time interval, you can simply build the time derivative of the distance traveled. You can write it like this: dx at time t over dt, or shorter, you use the dot above the variable, specifying the time derivative. Just to remember, that's time derivative, and this would be a spatial derivative. Okay, so we're talking about time derivatives all the time. Okay, now you can compute it the other way around as well. If you know the velocity, then you can compute the distance traveled when the car, for example, drives with a certain velocity. So we can transform the previous equation into x0, our starting position, plus integral over time of the velocity.
Could you please repeat this?
This equation?
Yes.
To compute the distance traveled after a certain time, we have to take the starting position, x0, according to our figure above, and add the integral over time from the starting time, which is 0 usually, to the current time, and integrate the velocity over time. V as time-dependent variable over time. dt is the variable, or specifies the variable which we use for the integration. Okay, then for the acceleration, it's quite similar. Dimension, again, maybe I should mention this. If you not remember, a distance is stated in meter, usually. Of course, you can also use kilometer, millimeter, whatever, depending on your specific problem. And velocity is stated in meter per second. How many meter does my object travel in how many seconds, or in a second? Okay. For the acceleration, the dimension is meter per square second. And to compute the acceleration, we have to build the time derivative of the velocity. So again, we can either write dv over dt, or we use the shorter way of stating it, v dot t. And then the time derivative, first time derivative of the velocity, corresponds to the second time derivative of the position or the distance traveled. And again, we can rearrange this equation to compute the velocity if we know the acceleration. So we have a starting a starting velocity, of course, and then we add the time integral from 0 to the current time at dt. Thank you for answering. Yes, I said I will, but not after every class. So probably after every chapter. Okay, now you do have a formulary, and you probably not all of you have it printed yet, of course, but we can have a look at it online. So this is our the front page of the formulary. You have the content there, and if you go to the first page, you have the point kinematics. And that's exactly what we're doing right now, chapter 1, what we just started, point kinematics, and we are in the subchapter 1.1, rectilinear motion. And here you can see all the equations that we just discussed. Okay? These 3 equations to compute the distance, the velocity, and the acceleration using the equations known. And now, of course, we can simplify our equations in certain situations. Now, for example, if I have an object moving with a constant acceleration here, okay? Then if my acceleration is constant, if I build the time derivative, if I build the time integral of a constant value, I simply have to multiply by t. To remember, if you build the integral of x over dx, I think this is what you're used to, okay? Then the result of this is 1/2 x squared. If you build the time integral of 1, you integrate the number 1 over x. The result is x. This is a variable depending on this parameter which we use to integrate. This is just a number, so it's constant, okay? And if our acceleration is constant and we apply this formula here, then we end up with velocity is equal to our initial velocity plus constant acceleration multiplied by the time. The acceleration itself does not change over time. And again, we can use this and apply it to this equation here. And then we obtain the distance traveled, which consists of the starting position, then the starting velocity multiplied by the time. And then if we integrate a times t over t, then we obtain 1/2 a t squared. Of course, you do not have to do these integrations. These are standard equations, okay? And you simply have to look them up. But you have to know where to find them. If you do not memorize them, then at least you have to know where to find these equations. Another special situation would be that our point mass is not accelerated at all. So we have an acceleration of 0, no acceleration. That means the velocity of the car does not change. It moves with constant velocity throughout the whole time interval. Now, if we integrate this to obtain the distance traveled, we obtain the equation below. The distance traveled consists of our starting position, of course, plus v0 initial velocity times time. And again, I'll just switch to the formulary. Rectilinear motion are only the first few equations here. You have, at first sight, it might seem to be very long equations, okay? But there are several equations in one. So this is the equation that I just wrote. The distance traveled in case of a constant acceleration. And this is the velocity traveled in case of a constant acceleration. Now, in case, I'm just writing on here, don't do this on your paper document, okay, in your paper formulary. In our case, if the acceleration, or if you have the second special case, if the acceleration is 0, well, then we just have a look at this equation, and if the acceleration is 0, then this term vanishes, and this term vanishes. Simply set a to 0, okay? And we end up to the second two equations that we just discussed. And behind these marked equations, you will find different ways of stating these equations. So substituting the time, for example, like here to erase the acceleration in the equations, etc. Okay, and below here is about it. It's just a rearranged equation from here to here, from here to here. That's just rearranging, taking the velocity on the other side and dividing by time. Okay, so this is basic math, but you should be able to read the equations, to understand the equations, and of course to apply these equations. Okay, let's get back to our script. And here we have a simple example. No, it's too big. Okay, we have this velocity time diagram given. So our point mass starts to move with 0 velocity at time t equals 0. So here is 0, and this is our initial velocity, or our starting velocity. And of course, it's also t equals 0. Then it is accelerated. It has to be accelerated because the velocity increases. The velocity increases until we reach the time t1. And afterwards, our point mass moves with constant velocity for the rest of the time that we are looking at here. And what we want to do is we want to derive the distance and acceleration as time-dependent variables, and the velocity and acceleration as variables dependent on the position, and the acceleration dependent on the velocity. We have two different types of motion. First, the process of acceleration, and then starting from t1, the constant velocity. So if we have a look at the first part of our velocity time diagram, then we simply apply our equation stated above. The velocity is v0 plus at, a times t. Since our point mass starts at a velocity of 0 meter per second, this is 0. And we can rearrange the equation to obtain the acceleration. A is equal to and for this point right here, the end, our first time interval, beginning of our second time interval, we can state that the acceleration can be computed from the velocity at this time divided by the time that we have reached then. So our velocity, our acceleration is constant. Okay, now we also want to compute the, well, that's the first part, actually wanted to compute the distance as time dependent variable. Now what we can do is we can state, as stated above, x is equal to x0 plus integral from 0 to t v dt. Now we know again that our starting position is 0. We do not yet know our velocity. But what we can do is we can apply or substitute this equation here for the acceleration, meaning that v is equal to originally a times t, and if we substitute the acceleration which we just computed, v1 over t1 times t. Okay, now let's apply this for the integral 0 to t. Now we're substituting the velocity by v1 over t1, which is just a constant, times t dt. So velocity over time t is constant, so we simply have to integrate t over dt, same as I just wrote for the variable x. So you know it's 1/2 t squared. And now we have the distance as time-dependent variable. Since our acceleration is constant, our result that is in the screen, that it just marked with the screen circle, corresponds to all these three results. Okay, it neither depends on the time, nor on the distance, nor on the velocity. It is constant for the first part of our velocity time diagram. Okay, now what else do we need? We still need the velocity dependent on the position. Now we have this equation right here, and the distance then does equal some constant times t squared. Now, what is t squared? Now again, we use this equation written in green and rearrange this equation for the time. I'll write it here. I'm talking about this equation. T is equal to T1 over V1 times velocity. Now I use this to substitute it for the time. Of course, I want the velocity dependent on position and not on time. So if we do that, we obtain x is equal to v1 to t1, then it's t squared, so t1 squared over v1 squared times the velocity, and then time cancels once, the velocity cancels once, and now I have position dependent on velocity, but what I want is velocity dependent on position. So I have to rearrange. Oh, sorry, I forgot the square here. I have to rearrange for the velocity, which is 2x v1 over t1. For the second part of the velocity time diagram, it is even simpler because there the velocity is constant. And that means that the time derivative of a constant is equal to 0. In consequence, our acceleration is 0. Remember what we just stated here. We can read from our diagram that the velocity is constant, and in consequence, the acceleration has to be 0. So A is 0, and velocity is constant. Now we need the distance, and for the distance, we apply the last equation marked in yellow above. So it's x is equal to, and now our starting position is not 0, because for our second type of motion, this motion starts at the red cross here. So our starting position corresponds to the position from the first part at time t1. And then our time integral starts at t1, runs until t, and we integrate. Here it's called v0, of course. In our case, it is 1 dt. Okay. Why there's okay, so there's a question in the chat. Could you please explain why there's a v squared for the last equation of I? V square here, probably. Here. It's because we have a t square. And then if we substitute t square, we have to square this here, and this results into a v square. Okay. So now,
Excuse me, Professor, just a quick question. Can you please repeat the last equation again?
this one?
Absolutely, yeah.
Yes, that's this one here. And so we have a zero acceleration. Okay. And this is the standard equation. But in our case, our starting position corresponds to this position that the object has reached at time t1. Okay. And that's why we have to use the position xi from our first case at the time t1. That's our starting position for the second type of motion. And then we have v0. Oh, wait. I didn't have to integrate. I made it more complicated and it had to be. Because if the acceleration is 0, we do not have to integrate. Then we have v0 times t, and v0 again is our velocity from the first case at time t1 multiplied by t. This I, corresponds to this the first part of the motion. That's why I. Okay, now we simply have to substitute as the last step our distance for the two situations of distance and velocity at time t1, and then we obtain 1/2 v1 t1 and plus where's my velocity here, v1 over no, wait. Okay. No, simply v1. It's just we have to use the Green equation. Okay, I will just state it here again. We have v1 over t1 times t, and we have to use this at time t1. So v at time t1 is simply v1 over t1 times t1, and this cancels. The time cancels. Of course, we could just simply read it from our velocity time diagram as well. So here we end up with v1 times t.
Sorry, here would we use t minus t1, since it's so t is the total time from 0, right?
The t is oh yeah, you're right, of course. Thank you very much. Exactly. T minus t1, because we are starting at time t1. And then, well, we can simplify this equation once more. So we would have v1 times t, okay, minus 1/2 v1 times t1. Could have used parentheses for v1, but doesn't really make a difference. Okay.
Yeah. Just, sorry to cut you. Just one thing. So to be more clear, when we talk about this over here, I can simply substitute this whole thing into this, right? It's the same thing.
It's the same thing, exactly. But then you have the velocity v, and you have to substitute the velocity for what you computed before. Of course, you have to substitute the velocity v1 for v, right? Here.
Okay, understood.
Then our final velocity at time t0. Okay, now what we can do, we can draw the different diagrams. Of course, for the acceleration, it's quite simple, because in the first part, the acceleration is constant, and in the second part, the acceleration is 0. So what we obtain is a curve like this. And of course, we could draw 3 of these, or we simply, well, yeah, let's draw. We can draw 3 times. Acceleration over distance, exactly the same, and acceleration over velocity as well. More interesting is the part for distance over time. Distance over times. And then here we have T1. And now it's a quadratic function for the first part until here. And then that's a linear function. And then similar for velocity over distance. I just answer to this in a second. Let me just draw the last diagram. Then again, we have here the square root for the first part, and then constant velocity for the second part. Here, referring to the question in the chat, right now we are talking about distances because we are simply discussing a point mass that moves through space. Okay, 2-dimensional plane right now, and so it travels a certain distance. Okay, a displacement makes more sense in strength of materials, maybe, when you have when your object deforms, things like that. Okay, so here right now we're talking about distances traveled. Yes, of course, you do not have to derive these equations all the time, and what you have to be able to do is apply the equation stated in the formulary. And of course, these are like the simple equations, and we made them become a bit difficult to the problem that was stated here. But it's just applying the equations stated in the formulary and rearranging according to the variables asked for.
Professor, can you please explain how do we get this form to this form?
Yes, here it becomes like a bit. You see this equation here, okay? I will write it a bit further, or maybe down below here. So what it says is x is equal to v1 over t1 times t squared. Okay, so this describes the distance traveled in the first situation over time from 0 until t1. So now I want to compute the distance that our object has reached at time t1. So what I do is I forget the x, sorry. I say, okay, how far did my object travel at time t1? So I have to substitute this by t1 square, and then this cancels. And then this results into 1/2 v1 t1. Okay?
Okay.
Okay, so this is our simplest form of motion. But of course, there is another quite simple form of motion, which is not the rectilinear motion, but the circular motion. The circular motion is also quite simple because we have basic equations to describe this type of motion. And now if we move on to the next page, we will talk. Sorry, my computer is a bit slow today. Okay, can you see it? Yes, should be. Okay, we will talk about the circular motion. Now, for the circular motion, we have a point mass that travels along a circular path. Okay, so this here is our circular path. There's a center about here. That's the center of our circular path, and this is our object. Might start here, for example. And now we will do exactly the same thing. We will describe the motion of our point mass in a certain time interval. This is our starting position, or the position when we start recording the motion. Let's say, again, it's t0, and to simplify the equations, we say it's at 0 seconds. Our circle has a certain radius, like this. Now, this point mass moves counterclockwise, for example, and it moves with an angular velocity and an angular acceleration. The angular velocity is written as omega 0 at time 0, okay? Our initial angular velocity. And our angular acceleration, initial angular acceleration, is alpha 0. Now, this object might have started earlier with its motion. So again, similar to the car that we discussed previously, it might has traveled a certain distance already. So we need a reference point, and this reference point could be here. And now we can say, okay, from our reference point, we already covered an angle of certain degrees, our angle phi 0, to describe our starting position. Just one side remark, because sometimes I get asked this question. This symbol is a phi, an angle. Some people get confused with this symbol. This is rho. Phi often used to describe an angle. Rho often used to describe a density. Okay, I'm always referring to this. Okay, now our point mass travels along this circular path, and sometime later it might be here. So this is our time t. Now it has an angular velocity omega t and an angular acceleration alpha t. And of course, the angle has changed in comparison to our previous position. So now we are at the angle phi t. Again, we need a sign definition. So often counterclockwise is considered as positive direction and clockwise as negative direction. And that's what I will state here. So this means rotation counterclockwise, positive phi omega alpha. once you chose your positive direction, you have to apply it to the angle, to the angular acceleration and angular velocity. Again, remember your right hand rule from Engineering Mechanics 1. You use your right hand, your thumb points upwards. Yeah, that means the plus sign, and your fingers show the direction of rotation. Okay, so this is our positive direction. Okay, and again, similar to the rectilinear motion, we have equations to describe these kind of motions. So we have, or we can compute the angular velocity. The dimension of the angular velocity is 1 per second, or radians per second. The angle itself is degree or radians, and the angular acceleration, radians per square second, or 1 per square second. Now, and as you probably already assume, we can compute the angular velocity by building the time derivative of the angle. And vice versa, we can compute the angle by summing the initial angle plus the time integral of omega t dt. Okay, then we can do the same for the angular acceleration, building the time derivative of the angular velocity leads to the angular acceleration, or building the second time derivative of the angle building the second time derivative of the angle leads to the angular acceleration as well. Yes, literature, there is a book called Engineering Mechanics 3. Just a second, it's A5 format, and von Groß, Hauger, and Schröder, and some others, Engineering Mechanics 3 or Dynamics. I will just quickly show to you. It looks like this. It exists in the library here in Schweinfurt, and it's quite a good book. I'll just write the authors as well in the chat. And there are also a lot of exercises in this book that you can use for additional practice. So okay, so so it's called Engineering Mechanics 3, and the authors are Groß, Hauger, Schröder. Okay, and you can get a book in this book in the library, or at a bookstore, or at Amazon or whatever. But of course, if you do not want to pay for it, I recommend the library. The small circle, like this small circle. Oh, here. Yeah. No, that's degree. So we would write it's 30 degrees. That's an angle. Or 90 degrees, which would be pi over 2. And if you state an angle in radians, then you usually state it dependent on pi. But of course, you can compute from degrees to radians. I'll just choose the edition that you can get. My edition is just second edition. It's what I have, but there are probably newer editions already. Okay. I don't know, actually. Check at the library if they have it as an ebook, maybe. Okay, now for the angular acceleration, again, we can compute the angular velocity if we know the acceleration, angular acceleration. Like this. Okay, and again, very similar to the rectilinear motion. These equations, in principle, these equations are identical. Only our variables are called different. Rectilinear motion, it's a distance traveled or position. Here, it's an angle. Rectilinear motion, it's a velocity. Here, it's the angular velocity. Rectilinear motion, it's an acceleration. Circular motion, it's the angular acceleration. But computing from angular velocity to angular acceleration is identical to computing from velocity to acceleration.
Hey, दिमाग खराब
Okay, then the small n refers to the rotational frequency or rate of rotation. The number of rotation is simply a number. It has no dimension. Okay. But the rotational frequency is usually stated in 1 per second, number of rotations per second or per minute or rounds per minute. So again, it's already almost stated here. N is 1 over 2 pi d phi dt. And we know if we build the time derivative of the angle, we obtain the angular velocity, meaning that our rotational frequency is obtained by omega over 2 pi. And we can rearrange to compute omega by 2 pi 1. Now, if we want to know the distance traveled of our object that moves along a circular path, we can compute the arc length of this object. And the arc length is computed by the symbol, the variable is called s. It's computed by radius of our circular path multiplied by the angle covered. So just the simple example of our object that we discussed above. We had T0 here. And then this is R. This is also R. Might have moved here. That's our circular path. At time t. So this is the angle, change in angle between these two positions. And then angle times radius gives this distance right here, the arc length. Yes, phi is for the number of rotations, phi is given in arc length, so dependent on pi. In all the situations that the angle is not stated within a sine, cosine, or whatever, you have to state the angle in radians and not in degrees. Otherwise, it would not work. Your dimensions wouldn't match. Okay, so just remember, for the angle stated in radians, except you use sine of phi or something like this, or you change your calculator to radians prior to computing this. We will discuss this when we have specific problems regarding this topic. Okay, one last look to the formulary, first page in the formulary. We discussed the equations for the point kinematics. Then below we have the circular motion. Again, here you can see the equations that we just stated in the lecture notes, then our special case for the constant acceleration. And of course, these equations here simplify even more if the acceleration is 0. The term containing the acceleration cancels. And so we have these equations. And below, also on this page, you can see our important parameters, meaning and assuming from now on that our starting position, our starting angle is 0, the path or arc length, and that's what we just did. What we still need to discuss is how to obtain velocity and acceleration. Okay, that's it for today. So we will continue here on Friday as online class, and then Monday next week we will have an online and an offline class as well. Okay, have a good day, and then see you on Friday. Bye.
Thank you. Thank you, Professor.
Thank you,
Bye.
Professor.
You're welcome.
Professor, like I just came a little bit late, so just can you just skip the pages before so that I can look at the things which you thought before?
I didn't understand your question.
I came a little bit late, so I just didn't see the. I was not here for the first lecture, so like, can you just go back like some pages so that I could see what you thought before?
That's where we started.
Okay. So just like linear motions and circular motion.
Exactly. That's all we did so far.
Okay, thank you.
Yeah, you're welcome.
Professor, I have a question for you.
Yes.
I would like to know here if we will be receiving a copy from the uni, or are we supposed to print our own?
A copy from what?
A copy of the lecture notes and the questions.
From the, yes, as I already said, I will give you the lecture notes, but not after every lecture, just every couple of classes. And of course, as you probably already realized, when there are questions, then I will write into these lecture notes, and they might become a bit messy. So just don't rely too much on the lecture notes that I will upload.
Excuse me, Professor, that was not my question.
Oh, sorry.
Yeah, I got my answer a long time, but what I mean is, like, you know, I thought I can print the notes so that it's easy to write down.
Yes.
So some lecturers, they get it done from the uni and they give it to us.
Yes, that's what I do as well. Are you logged in the e-learning course?
Yeah, I am.
Did you receive yesterday's email?
Actually, I logged in yesterday.
Yeah, okay, then, because it's written in the e-learning course and then sent an email to all the students in the e-learning course how to get the lecture notes and exercise book and all this stuff. So you can pick it up on Wednesday, this week only, from 4 to 4:30, or Monday during our offline class.
All right, so I believe during, what do you call, it's in the library, right?
No, in my office.
In your office, okay, at Wednesday at 4 o'clock, 4:30.
Between 4 and 4:30.
All right, okay.
Okay?
See you on Wednesday.
All right, see you.
Thank you.